Come on, my dears, let us proceed further in chapter number 5. Kindly read this statement of illustration number 4. Read it? Look. Angular speed of electron revolving in nth circular orbit of hydrogen atom is given to us in the statement as omega equals to pi m e raised to 4 upon 2 epsilon 0 square n cube h cube. Just give me identification of each quantity. Come on, m is mass of one electron, E is magnitude of charge of one electron, epsilon 0 is permittivity of vacuum. What about small n? It is called order of orbit, or it is also called principal quantum number. Come on, small h is Planck's universal constant, correct? Fine. And now, omega formula everybody knows, omega equals to 2 pi f or 2 pi upon capital T, because f is 1 upon t. Come on, omega formula in terms of periodic time is omega equals to 2 pi upon capital T. Fine. This right hand side I have written as it is. Now pi ones are pi. Okay. We are asked to find out principal quantum number n. So we should make subject of the equation from here, say n cube. First of all, make n cube as subject of equation. Come on. N cube we may transfer here. So it will be, come on, m e raised to 4 into capital T, 2 2s are 4, epsilon 0 square h cube. If you make n cube as a subject of equation, you will get this right hand side. Come on, now put up all the values. Mass of one electron 9.1 into 10 raised minus 31 kilogram. Magnitude of charge of one electron 1.6 into 10 raised minus 19 Coulomb. It's a fourth power, don't forget. And what about capital T? Periodic time of revolution at present they have given in the statement equal to periodic time of revolution of geostationary satellite, about which you had studied in second semester. Just recall, what was geostationary satellite? Geostationary satellite is that artificial satellite which revolves around Earth in an equatorial orbit with orbital periodic time just equal to periodic time of rotation of Earth about its own axis. And that periodic time, you know, it is 24 hours, and that time from hour I must convert into second. 1 hour, as you know, it is 3600 seconds, correct? So right now this orbital periodic time of electron, we are supposed to take orbital periodic time of geostationary satellite, which is 24 hours, and when you convert into second, you must multiply by 3600. Sure? Now divided by 4, what is epsilon 0? Permittivity of vacuum, it is 8.85 into 10 raised to minus 12 Coulomb square upon Newton meter square. It's a square. What about h? Planck's constant, 6.625 into 10 raised to minus 34 joule into second, and it's a cube, correct? Fine. Now if you simplify this, answer is 565.63 into 10 raised to 18, but this is not n, it is n cube. We want only n, so we should take cube root on both the sides. Come on, when you take cube root here, it will be n. When you take cube root here, 565.63, put it in bracket, all raised to 1 by 3. And when you take cube root of this, you are supposed to take raised to 1 by 3. 3 6 are 18. So here it is 10 raised to 6. Cube root of 10 raised to 18 is 10 raised to 6. And now cube root of this, from log table you will get the answer 8.27. This 10 raised to 6 as it is, correct? So if you speak out this value in words, it is 82 lakhs 70,000. 82 lakhs 72,000. 82 lakhs 70,000. 82 lakhs 70,000. Correct? Now what does it mean? See, as you move away from nucleus, the order of circular orbit goes on increasing. Correct? The way we are taking around nucleus, say n equal to 1 orbit, then n equal to 2 orbit, n equal to 3 orbit. That way you just take which order? This much. It's a very high order, 82 lakhs 70,000th orbit. 82 lakhs 70,000th orbit. Now if you move this much away from the nucleus, and then in that orbit it will so happen that electron is revolving that slowly, such that it takes 24 hours to finish one circulation. This is the meaning. Okay, fine. Now, how to get cube root of this? I am showing you using log table. How will you get it? I am showing you. This value you want to find out. Correct? Take it as x. So x equals to 565.63 whole raised to 1 by 3. Take now log on both the sides. Log of x, it will be, log of a raised to x, it becomes x log a. So this power will become multiplier 1 by 3 into log of this part, log of 565.63. And now 1 by 3 as it is. And if you find out characteristic for this figure, it is 1, 2, 3 digits are there before decimal point. Out of 3 you are supposed to subtract 1, 3 minus 1, that is 2. So characteristic is 2. What about mantissa? Mantissa you will find out this way. Against 56 in the log table for logarithm tables, come on, against 56, below 5, difference of 6 you will add. Against 56, below 5 and difference of 6 you will add. Then you will get the value 7525. Altogether, logarithm of this figure comes out to be 2.7525. And that value divided by 3, answer is 0.9175. 0.9175. Okay, fine. Once you know log x, then if log x equals to something, then x will be antilog of something. X will be antilog of this part. It comes out to be 8.270. 8.270. Correct? So value of cube root of this comes out to be 8.27. 8.27, and this multiplied by 10 raised to 6. This much is the value of n, that is principal quantum number or order of circular orbit of electron. Got it? Fine. Now kindly read the statement of illustration number 5. Come on, read it. Look. Recall the formula for radius of nth circular orbit of an electron. It was r equals to epsilon 0 n square s square upon pi m z square. Remembered? Fine. Now accept n square and z, rest of the quantities are constants. So if you remove rest of the part, then you can write r proportional to n square upon z. I repeat, except n square and z, rest of the quantities are constants. So if you remove them, then you may write r proportional to n square upon z. R proportional to n square upon z. Then with n square it is direct proportionality, with z it is inverse proportionality. And now you may write mathematically from here r1 upon r2 will be equal to n1 square upon n2 square into z2 upon z1. Z2 upon z1. With n square it is direct proportionality, so 1 to 1 to. With z it is inverse proportionality, so 1 to 2 1. Okay, fine. Now here what are you given in the statement? That orbital radius of electron in the ground state of hydrogen atom and orbital radius of electron in beryllium atom for some particular order become equal. So here they have given R1 equals to R2. These two radii they have given in the statement as equal. When these two are equal, naturally ratio will be 1. What is this N1? It is order of orbit of electron in first element. First element I have taken hydrogen, second element I am taking beryllium. And for hydrogen they are given ground state, so N1 is 1. What about N2? That is what we require. So N2 square as it is. What about Z1? Atomic number of first element, because first element is right now hydrogen. Atomic number for hydrogen you know it is 1. So Z1 is 1. And what about Z2? Atomic number of second element, which is right now beryllium. From periodic table you must be knowing from chemistry. For beryllium the atomic number is 4. So Z2 is 4. Now simplify. N2 square you may take here. N2 square will be 4. If N2 square is 4, take a square root on both the sides, then N2 equals to 2. Correct? Fine. So you can say orbital radius of electron in the second state of beryllium atom and orbital radius of electron in the ground state of hydrogen atom are equal. Now we are asked to compare the total energy values of electron in these two states for these two elements. Let us compare. Come on, recall the formula of total energy of electron in nth circular orbit. It was En equals to minus mz square e raised to 4 upon 8 epsilon 0 square n square s square. Wait. Except z square and n square, rest of the quantities are constants. So if you remove them, then En proportional to z square upon n square. En proportional to z square upon n square. Come on, mathematically what do you write now? Next step, En1 upon En2 equals to z1 square upon z2 square multiplied by n2 square upon n1 square. Just kindly notice carefully. This is directly proportional to this. So here 1 2 1 2. But with n square it is inverse proportionality relation. So here 1 2 and here 2 1. Okay, fine. And now this ratio we require, so leave it as it is. What is Z1? Atomic number of first element. Because first element is hydrogen, atomic number is 1. Z1 is 1. Z2 is atomic number of second element, which is right now beryllium, for which atomic number is 4. So Z2 is 4. It's a square, don't forget. What is N1? Order of orbit of electron in the ground state of hydrogen element. Hydrogen atom. Come on, for ground state, what is the order of orbit? It is 1. So N1 is 1. And what is N2? N2 we have found out, it is 2. N2 is 2, it's a square. Now just simplify. 2 square is 4. 4 square is 16. 4 upon 16, it is 1 by 4. Correct? Now take this En2 here. Take this 4 over here. Then En2 will be 4 into En1. What does it mean? That total energy of electron in the second state of beryllium atom is 4 times total energy of electron in the ground state of hydrogen atom. This is how we have made the comparison between two energy values. Okay. Kindly read this statement of illustration number 6. Come on, read it. Look. We are talking about Bohr series for hydrogen atom. What was the formula for finding wavelength of spectral line in Bohr series for hydrogen atom? Remember that formula? 1 upon lambda equals to R into bracket 1 upon 2 square minus 1 upon n square. Here it is 1 upon lambda equals to R into 1 upon 2 square minus 1 upon n square. What are the values of n? Values of n are after 2 all the positive integers. After 2, what are the positive integers? Come on, 3, 4, 5, 6, dash up to infinity. Fine. And now, when you are talking about H alpha line, you should take first value in this series, that is n equal to 3. For H alpha line, n equals to 3. For H beta line, n equals to 4. For H gamma line, n equals to 5. For H delta line, n equals to 6. For H infinity line, n equals to infinity. Correct? Here we are given H alpha line, so we should take first value, that is n equal to 3. Wait. At present I am talking about hydrogen atom. So instead of lambda, I am just putting lambda H, H for hydrogen. Okay. Instead of R, I am putting RH. This is the Rydberg constant for hydrogen atom. Okay. Fine. You know, for different atoms, the nuclear mass would be rather different, and depending upon that, Rydberg constant slightly varies. Okay. So for hydrogen atom, I am just putting symbol RH. Wait. You are talking about H alpha line, for which n equals to 3. Put it here. N equals to 3. Now this 2 square is 4. 3 square is 9. And this 1 upon lambda H as it is, RH as it is. Just simplify. LCM will be 36. Here it will be multiplied by 9. Here it will be multiplied by 4. 9 minus 4, that is 5 into RH upon 36. Take reciprocal now. If you take reciprocal here, you will get it lambda H. When you take reciprocal here, it is 36 upon 5 into RH. Give it equation number 1. Correct? Here we are talking about hydrogen atom. Now another atom is given to tritium, which is isotope of hydrogen. Isotope of hydrogen, having mass 3 times the mass of hydrogen. Okay. So for another atom, which is tritium, instead of H, you just write T. So from here, lambda T will be 36 upon 5 into RT. 36 upon 5 into RT. What is this RH? Rydberg constant for hydrogen atom. What is this RT? Rydberg constant for tritium atom. Okay, fine. And why we could write this similar formula here also? Because for tritium also we are looking for H alpha line. Correct? Spectral line remains same in both the atoms. Okay. Now suppose I want difference between these two wavelengths, then I should take the difference this way. Suppose lambda H minus lambda T. Lambda H minus lambda T, it will be this minus this. But when you take this minus this, 36 upon 5, 36 upon 5 can be taken common. 36 upon 5 is taken common. Inside the bracket, 1 upon RH minus 1 upon RT. 1 upon RH minus 1 upon RT. Simple. But just recall the Rydberg constant for a given atom. It was R atom equals to R infinity upon 1 plus M upon M atom. Instead of M atom, I am just writing M. Instead of R atom, I am just writing R. This is Rydberg constant for given atom. This is mass of that atom. Small m is mass of one electron, and this R infinity value is constant 1.09737 into 10 raised to 7 meter inverse. Wait. Now just take reciprocal on both the sides. So when you take reciprocal here, it will be 1 upon R. When you take reciprocal here, the denominator will appear in the numerator, numerator will appear in the denominator. So just take reciprocal here, 1 plus M upon M divided by R infinity. And now just write this formula for these two values. Come on. Start with this difference, lambda H minus lambda T. 36 upon 5 as it is. Come on, 1 upon RH. 1 upon RH. Instead of R, when you write RH, here instead of M, you should write MH. Come on, tell me, 1 plus M upon MH. 1 plus M upon MH divided by R infinity as it is, minus, I want now 1 upon RT. So instead of R, when you write RT, here instead of M, you should write MT. So 1 plus M upon MT. 1 plus M upon MT upon R infinity. Fine. But now mass of tritium atom, they have given in the statement, it is 3 times mass of hydrogen atom. Mass of tritium, please remember now, mass of tritium is 3 times mass of hydrogen atom. So in place of MT, we can write 3 into MH. Here we can write, okay, but before that, 1 upon R infinity, 1 upon R infinity can be taken common. So start with this difference, lambda H minus lambda T. lambda h minus lambda t should be equal to 36 upon 5 into r infinity. 36 upon 5 into r infinity. Inside the bracket, come on, 1 plus m upon mh minus 1 minus plus minus m upon mt. But 1 minus 1 will cancel. M upon mh, m upon mh minus m upon mt, m upon mt, m upon mt, m upon mt. But mt is how much? 3 into mh. mt is 3 into mh. Correct? And now tell me, m upon mh we can take common. So this part as it is, m upon mh taken common. Inside the bracket, left from here is 1 minus left from here inside the bracket is 1 by 3. 1 minus 1 by 3 means what? 2 by 3. So here I have written 2 by 3. Now just dictate me the respective values. 36 as it is, mass of 1 electron 9.1 into 10 minus 31 kilogram. This 2 as it is, come on, 5 as it is. What about R infinity? Just now I told 1.09737 into 10 raised to 7 meter inverse. What about MH? Mass of hydrogen atom. Mass of hydrogen atom, we will take mass of its nucleus, and inside the nucleus of hydrogen atom there is only one proton. So actually you should write here mass of one proton, which is 1.6 into 10 raised to minus 27 kilogram. 1.6 into 10 minus 27 kilogram, mass of proton or mass of hydrogen nucleus or mass of hydrogen atom, they are nearly equal, and into 3, correct? Fine. Now just simplify. Answer is 2.38 into 10 raised to minus 10 meter, but 10 raised to minus 10 meter is nothing but 1 angstrom. So this difference in the wavelengths is 2.38 angstrom. Tell me, what have you got? Come on, difference in the wavelengths of H alpha line from hydrogen and tritium atoms. And why these wavelengths differ? Because this is the formula for finding that wavelength. But if Rydberg constant is different slightly for different atoms, naturally lambda would differ. And because lambda value is different for hydrogen atom, different for tritium atom, then we should get some difference which should be non-zero, correct? And that difference which we got right now, it is 2.38 angstrom. You may be asked to find out such difference for pair of another two atoms, correct? Here we are finding this difference for hydrogen and tritium atoms, okay? Now my dears, we are going to discuss very important theoretical article. Look at the title: Quantization of energy, radius of orbit and angular momentum for electron orbiting in, right now we will take hydrogen atom, okay? Fine. Now tell me, first of all, what do you mean by quantization of any physical quantity? Quantization of any physical quantity means if any physical quantity can assume certain specific, certain discrete values only, and it cannot assume remaining values, then that physical quantity is said to be quantized, correct? Mr. Bohr, in his Bohr's atomic model, had made first postulate, first assumption, first hypothesis was out of innumerable number of circular orbits that we may consider around nucleus. He said electron can revolve only in those circular orbits where electron has angular momentum equal to nh upon 2 pi, correct? If angular momentum of electron is assuming only certain specific values, means you can say angular momentum of, orbital angular momentum of electron is quantized. So this concept of quantization which he had assumed, later on we found it to be true also. So really it is like that, the electron can assume only certain specific values of orbital angular momentum, fine. But this quantization of angular momentum of electron, Mr. Bohr had proposed on the basis of classical physics. But now, let us follow now wave mechanics. In wave mechanics we have studied in third semester. Mr. de Broglie had said that whenever any tiny materialistic particle is in motion, it behaves like a wave, correct? And that wave is known as matter wave or de Broglie wave, and he had given the formula for finding de Broglie wavelength. Remember that formula from third semester, lambda equals to h upon mv. So now question arises that when electron is orbiting in a particular orbit, at that time also electron is a tiny particle, it is in continuous motion, so at that time it also must behave like a wave. So if really electron has that wave characteristic at that time, then can we achieve the quantization of angular momentum? This is the question. Let us see whether we can get it or not. We will get it. Look here. Suppose electron is orbiting in this circular orbit, okay, and at that time, according to de Broglie, it behaves like a wave having wavelength lambda equals to h upon mv. Fine. Now, if we want to represent the motion of electron, that is right now orbital motion of electron, by a wave, that wave should be stationary wave. That wave should be stationary wave, because if electron is moving in this orbit, and if this is permitted orbit or Bohr orbit or stationary orbit or allowed orbit, then you know electron while circulating in permitted or allowed orbit, it does not emit any energy. And you have studied in second semester about stationary waves. During the propagation of stationary waves, the energy remains in the same dimension of the medium, it does not get emitted, okay. So if energy is not emitted, then the orbital motion of electron must be represented by a stationary wave, one thing. Second thing, that wave should be such that from whichever point if we start, suppose from this point, correct, then we should come back to the same point, that is that stationary wave should be made closed, then only the probability of finding electron at a given position would remain same at all the times, okay, fine. For that sake, we should assume the orbital motion of electron to be represented by such a stationary closed wave, okay. Now let us see our argument is proper or not. Let us see. At present, I have represented moving electron by some integer number of waves, At present in the figure, you will find 6 number of waves. How many? 6. How? Look here. 1, 2, 3, 4, 5, 6. Not necessary that you also must draw the figure and you also must show only 6 number of integer waves. Not necessary. Depending upon different states of electron, you may have shown this different number of integer waves. No problem. Here I have shown 6 number of waves. Fine. Now tell me, if wavelength of wave is lambda, then if there are n number of integer waves selected on this circumference of this orbit, then if such a motion of electron is to be represented by such a wave in which there are n number of integer waves, then tell me what should be length of circumference. Come on. For one wave, what is the length? Length is equal to lambda. For n number of integer waves, what will be the total length? N lambda, correct? But that total length would be equal to circumference of this orbit. And circumference of circular orbit having radius r is how much? It is 2 pi r, correct? Fine. Now, if the orbital motion of electron is represented by such a stationary closed wave having n number of integer waves, each having wavelength lambda, then let us see whether we can get quantization of angular momentum or not. I am showing you. This 2 pi r as it is, and as it is, according to de Broglie, this orbiting electron behaves like a wave having wavelength lambda equals to h upon mv, correct? And now tell me, transfer this mv here, transfer this 2 pi in the denominator on right hand side. So it will now mvr, will be equal to NH upon 2 pi. MVR will be equal to NH upon 2 pi. MVR equals to NH upon 2 pi. What is this M into V? Mass into velocity is linear momentum. This is perpendicular distance of electron from the axis of rotation, and then momentum into perpendicular distance. Momentum into perpendicular distance will give you moment of linear momentum, and moment of linear momentum itself is known as angular momentum, shown by symbol L. So L equals to NH upon 2 pi. L equals to NH upon 2 pi. What do you mean by NH upon 2 pi? What is N? Order of circular orbit of electron, or it is also called principal quantum number, which changes in the integer way. N equals to 1, 2, 3, 4 dash dash dash. Because values of N are specific, here orbital angular momentum values also will be specific. If any physical quantity can assume only certain specific values and not the remaining values, that quantity is said to be quantized. So here orbital angular momentum of electron is quantized, correct? So though we assume wave characteristic of orbiting electron, then also we get quantization of angular momentum. And now tell me, in Bohr's atomic model, when angular momentum was taken this much, such orbits were called, come on, allowed orbits, or permitted orbits, or stationary orbits, or you may call Bohr orbits, correct? At that time, what was the formula for radius of circular orbit? Formula was R equals to epsilon 0 n square s square upon pi m z square. And there also, come on, values of n are changing specifically. So values of radius of circular orbit of electron are also quantized. And what was the formula for total energy of electron in nth circular orbit? That formula was En equals to minus mz square e raised to 4 upon 8 epsilon 0 square n square s square. In that also, if values of n are changing specifically, then values of total energy of electron also will change specifically. And so you can say total energy of electron is also quantized, because it assumes certain specific values only, not all the values, correct? So remember, the orbiting electrons, they behave like waves, and then using this wave characteristic, using this wave properties of electron, then also we can get quantization of total energy, quantization of radius of circular orbit, and quantization of angular momentum also, correct? Fine. Now kindly read the statement of illustration number 7. Come on, read it. Look, for hydrogen atom, atomic number is 1. When electron is revolving in circular orbit around nucleus, then you know the centripetal force is required, which is provided in the form of electric force, which obeys Coulomb's law. We call it Coulombian force. So right now centripetal force is equal to Coulombian force. Centripetal force is given by this formula, mv square upon r. What about Coulombian force? K q1 q2 upon r square. Instead of small k, I am writing 1 upon 4 by epsilon 0. Instead of q1, I am writing magnitude of charge of 1 proton in the nucleus of hydrogen atom. And what is this E? It is q2, which is magnitude of charge of 1 electron, which is orbiting in that hydrogen atom around nucleus. And divided by r square. Simplify now. R1 is r. Okay. So left is mv square on left side. And here 1 upon 4 pi epsilon 0 as it is, E into E, that is E square upon R. And now tell me, take here just multiplication with M on both the sides. Multiply by M into M, that is M square into V square. And here, come on, M is square upon 4 pi epsilon 0 R. 4 pi epsilon 0 R. I just multiply by M on both the sides. M into M will be M square, and here I have multiplied by M. Now take square root on both the sides. Square root of this will be m into v. Square root of this will be under root of m e square upon 4 pi epsilon 0 r. Wait, we are looking for de Broglie wavelength. What is de Broglie wavelength? Lambda equals to, by formula, h upon m into v. H upon m into v means what? H into 1 upon mv. H into 1 upon mv. 1 upon mv means reciprocal of mv. Reciprocal of this would be reciprocal of this, which is under root of, write denominator term in the numerator, write numerator term in the denominator. So under root of 4 pi epsilon 0 r upon m e square. H, Planck's constant, 6.625 into 10 raised minus 34 joule into second into under root of 4, pi value is 3.14. What about epsilon 0? Permittivity of vacuum, which is 8.85 into 10 raised minus 12 Coulomb square upon Newton meter square. What about small r? That is radius of circular orbit of electron in hydrogen atom. They have given in the statement, come on, 5.29 into 10 raised minus 11 meter. What about small m? Mass of one electron, which is 9.1 into 10 raised minus 31 kilogram. What about small e? Magnitude of charge of one electron, which is 1.6 into 10 raised minus 19 coulomb. Don't forget to make it squared. Okay. Simplify, you will get the value of lambda as 3.328 into 10 raised minus 10 meter. But you know, 10 raised minus 10 meter is nothing but 1 angstrom. So this is as good as 3.328 that many angstrom. Correct? Now wait. What does it mean that lambda value is this much? What does it mean? I am showing you. You know, when orbiting electron behaves like a wave, this condition is satisfied by Bohr radius. Bohr radius is radius of Bohr orbit, and radius of Bohr orbit is such that it satisfies this condition. Which condition? 2 pi r equals to n lambda. 2 pi r equals to n lambda. And now just find out n from here. 2 pi r upon lambda. 2, value of pi is 3.14. What about small r? Radius of circular orbit, which they have given in the statement. Come on, it was 5.29 into 10 raised minus 11 meter. What about lambda? We have got it 3.328 into 10 raised minus 10 meter. And now if you simplify this value, you will get 0.998. What do you mean by 0.998? Which is nearly equal to 1. So what do you mean by n equal to 1? N equal to 1 means what? Principal quantum number is 1 means what? It indicates ground state of electron. Which state? Ground state of electron. So what does it mean? That in the ground state of electron, which is orbiting in hydrogen atom, it so happens that it behaves like that sort of wave whose de Broglie wavelength is just equal to 1 circumference. Just equal to 1 circumference. Because when you will write n equal to 1 here, then lambda will be 2 pi r. Lambda will be 2 pi r. What is 2 pi r? It is 1 circumference. Got it? Fine. Suppose we get value of n equal to 2. Suppose. Then you may put here 2. Correct? So that 2 you can take down. So at that time lambda will be half of circumference. Half of circumference. Got it? But right now we are getting n equal to 1. Put it here. Then at that time the orbiting electron behaves like that wave whose de Broglie wavelength is just equal to 1 circumference. Okay, fine. Now, very good article. From the textbook description, you may not understand that much, and the important formula which are to be utilized in the numericals, in the MCQs later on in the same chapter, they have not given in this article, which are essential. Okay, better you try to understand from here. What is called excitation energy? Excitation potential. What is called ionization energy? Ionization potential. First thing, they have committed a serious mistake in textbook. They have taken potential as energy. It's very wrong. Potential and energy, they are not identical physical quantities. You know, energy unit is joule or electron volt, and unit of potential is volt. Both of them are very different. So don't take them as synonymous, please. First of all, let us try to understand what is called excitation energy and excitation potential. Remember, formula of total energy of electron in hydrogen atom in electron volt. It was given by this formula. In the last lecture we have seen this formula. Come on, En equals to minus 13.6 upon n square, that many electron volt. Now, what is this small n? It gives you order of circular orbit of electron, or it gives you principal quantum number, which changes like 1, 2, 3, 4, dash, dash, dash. Put n equal to 1, then minus 13.6 upon 1 square is 1. It will give you energy value, come on, minus 13.6 electron volt, correct? Put n equal to 2 here, come on, 2 square is 4, minus 13.6 upon 4. For n equal to, here it is, n equal to, then minus 13.6 upon 4, it is minus 3.4 electron volt. So, what I mean to say, in this formula you may go on putting values of n 1, 2, 3, 4 dash 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 up to infinity. Corresponding values of total energy of electron you can find out from this formula, and those energy values if you just show on the vertical y-axis, then the diagram prepared so is called energy level diagram. Last time also I had plotted the same diagram. So, here I am writing energy level diagram for hydrogen atom, correct? For n equal to 1, what is the total energy? Minus 13.6 electron volt. For n equal to 2, it is minus 3.4 electron volt. For n equal to 3, minus 1.51 electron volt. For n equal to 4, minus 0.85 electron volt. For n equal to 5, minus 0.54 electron volt. For n equal to 6, minus 0.37 electron volt. And if you write here n equal to infinity, then something upon infinity would become 0. So, for n equal to infinity, this total energy is 0. Okay, fine. Now, in this circumstances, what do you mean by excitation energy? Is very simple. If electron is lying in any energy level, say in ith energy level, having energy EI, correct? I means initial, I means initial. And suppose that initial energy level is this, okay, fine. From this state, if you supply that much energy from outside to that electron such that it may transit in any one of these upper energy levels, then that energy supplied is known as excitation energy, and that energy is to be supplied through some potential difference. That necessary potential difference is known as excitation potential. Energy supplied is called excitation energy, and the potential difference through which electron requires to be passed, that potential difference is called excitation potential. Come on, how would you define it? I am showing you. If electron is going from ith state, that is from initial state to say this final state, suppose, correct? Then here you may take energy as EF, correct? So, this is final energy, this is initial energy, final minus initial, that is increase in the energy of electron, got it? With whatever supplied energy, we can raise the energy level of electron. That supplied energy is known as excitation energy, and corresponding potential difference is called excitation potential. So, how would you find out excitation potential in volt? Simple. This energy difference, suppose you are finding in electron volt, that is in EV, and that EV value if you divide by E, naturally the unit will be volt, okay. So, when excitation energy is divided by magnitude of charge of one electron, the answer is going to give you excitation potential, fine. Suppose electron is lying here, correct? You want to send it to here, say from first state to second state. You will require energy to be supplied how much? Come on, this minus this. If you take this minus this, come on, EF minus EI, this minus this, minus minus plus. So, it is 13.6 minus 3.4, answer is 10.2 electron volt. So, when you supply 10.2 electron volts of energy to the electron lying in the ground state in hydrogen atom, it will be getting just transferred to second energy level. So, it makes a transition from first state to second state, and because it is going to upper energy level, it is said to be excited, and that's why that energy supplied is known as excitation energy, and corresponding potential difference is called excitation potential. Fine. Now, what about ionization energy and ionization potential? Suppose electron is lying here, है ना, having energy how much? Minus 13.6 electron volt. And suppose I am supplying energy to that electron, say 13.6 electron volt from outside. So, what would be its total energy? Minus 13.6 it has. What I am supplying to it? 13.6. So, total will be minus 13.6 plus 13.6, that would be 0. And when total energy becomes 0, come on, principal quantum number has become infinite, meaning thereby it has gone at infinite distance from the nucleus, you can say, correct? And once it is going to infinite distance from the nucleus, means it will be freed from the binding with the nucleus. And whenever any neutral atom loses electron, whenever any neutral atom loses electron, it will be transformed into positive ion. That's why that minimum energy supplied to it is known as ionization energy, and corresponding potential difference is called ionization potential. Wait, when electron is lying here, how much energy you are supplying? Plus 13.6, meaning thereby modulus of this, correct? Modulus of this. So, if electron is lying in initial state, say ith state, and at the time its total energy is EI, then what minimum energy should you supply to that electron such that it escapes out of the binding with the nucleus, it becomes completely freed, it becomes free electron, and the neutral atom gets transformed into positive ion. That minimum energy to be supplied from outside is modulus of EI. So, whenever electron lying in any state is just supplied from outside, energy equal to modulus of total energy in that state, then its total energy becomes 0, and at that time it is freed from the binding with the nucleus, and because neutral atom loses electron and gets transformed into ion, we call it ionization energy. Remember, ionization energy is not simply energy, it is minimum energy. It is minimum energy. If you supply energy to this electron, say more than 13.6, then also you can make it freed, but then other values of energy which are higher than 13.6 electron volt, they are not ionization energy values. Ionization energy value is the minimum energy to be supplied to electron lying in a given energy state. Suppose electron is already lying here and you want to make it freed and you want to supply ionization energy, that ionization energy to be supplied is just equal to modulus of this. What is modulus of this? It is 3.4 electron volt. What is ionization energy for third energy level? Come on, modulus of this, which is 1.51 electron volt. Simple. That's why written here, ionization energy is simply modulus of total energy of electron in the initial state. And corresponding potential, if you require, then that value you should measure for energy, you should measure it in electron volt. And if electron volt is divided by E, that answer will be in volt, which is called ionization potential. Ionization potential. For example, if electron is lying here and you want to make it freed from the binding with the nucleus, what minimum energy should you supply from outside? Plus 13.6 electron volt, which is modulus of E1. Modulus of E1. Such energy is called first ionization energy. First ionization energy. If electron is here and you are supplying energy from outside, say plus 3.4 electron volt, which is modulus of E2, then the atom will get transformed into ion. Then that energy, which is mod of E2, is called, come on, second ionization energy. Similarly, tell me, what is third ionization energy? Third ionization energy is 1.51 electron volt. Fourth ionization energy is 0.85 electron volt, and so on. Got it? And if ionization energy is divided by magnitude of charge of 1 electron, the answer gives you ionization potential. Got it? Practically, we find that for all the inert gases, values of ionization energy is maximum. What does it mean? They are very strongly bound with the nucleus. That's why they require maximum energy to be supplied to them, then only those atoms will get transformed into ions. So inert gases have got maximum values of ionization energy and hence maximum values of ionization potential also. Got it? See, last time we had studied about atomic spectrum, correct? Now you may obtain atomic spectrum for any atom made up of any element. There are certain points which are found to be common, okay? So certain characteristics are common and is found to be in general. What are those general characteristics? I am showing you one by one. First, position of spectral line, position of given spectral line is found to be same every time. See, when you are talking about atomic spectrum of given atom and you are talking about given spectral line, its position in the spectrum is found to be same every time. Whether you perform experiment today or after 2 months or after 5 years, the position would remain same, correct? Fine. And where you will get a given spectral line, that depends on type of element, and you know type of element again depends on atomic number. Fine. Second characteristic is that density increases, then intensity of spectral line also increases. In the discharge tube, if you fill up gas with more density, then all the emitted radiations have more intensity, and that's why the spectral lines obtained on the photographic plate also have more intensity. Third point is this: intensity of spectral line changes with the temperature. As you keep different temperatures of the gas filled in the discharge tube, then the value of intensity in the spectral line is also getting changed. And last characteristic, what will be the type of spectrum and how many number of spectral series we will obtain in a spectrum, that depends on how many valence electrons are there in the atom. For different atoms, if they are having different number of valence electrons because they are made up of different element, then depending upon the number of valence electrons, you may have different type of spectrum. We will see just now, there are two types of spectrum. One is emission spectrum, another is absorption spectrum. And in that spectrum also, how many number of spectral series would you obtain, that is decided by number of valence electrons in the atom. See, there are two types of spectrum. One is called emission spectrum, another is called absorption spectrum. The one which we had studied last time, and that spectrum, it was obtained after emission of radiant energy from discharge tube, and hence it is called emission spectrum, correct? In that, how the radiations are emitted, you must have remembered, electrons were making transitions from lower to higher energy states, but in higher energy states they are rather excited. They remain there only for a very short time, approximately 10⁻⁻8 seconds, and then after they make transitions into lower energy states, and at that time they emit some radiations. And because after getting emission we are obtaining that spectrum, we call it emission spectrum, correct? Fine. Now today we will understand about another type of spectrum which is called absorption spectrum. In the textbook they have not drawn any figure, so you may not understand that much. Better you concentrate here. All the necessary figures are nicely drawn over here. Please concentrate on the screen now. Look here. What do you mean by absorption spectrum? Consider a continuous radiation. Continuous radiation means having all the wavelengths, correct? You know, out of Vibgyor, in which there are 7 colored light rays, I have here 6 colored light rays. So I have shown only 6 colored light rays: violet, blue, green, yellow, orange, red. Okay. And now just make incidence of this continuous radiation on some photographic plate. Then you know photographic plate is a black, and on whichever region the radiation is made incident, that much region turns out to be white. So here in this much part we will have exposure of this radiation onto this photographic plate, and that's why that much part turns out to be white. We may call this white region as spectral band, not spectral line. It is a very wide region. You may call it spectral band. Okay. Now tell me, you do one thing. Consider atoms of gas filled in a tube which are lying in ground states. Suppose all these atoms are lying in the ground state, that is in the state of minimum energy, and then we make same radiation incident over that tube. Okay, same radiation is made incident here. You know what happens now? Out of this many radiations of different wavelengths, it so happens that these atoms, they just absorb only certain specific radiations with a specific wavelengths, and they do not absorb the remaining radiations. So naturally, if this radiation is suppose absorbed, then it will not be getting transmitted, correct? And if it is not coming outside from this tube, naturally in just opposite position you will have no incidence of radiation. That's why that much part of photographic plate will remain black, and because of that here we get black line, very thin black line we get over here. Similarly, suppose this radiation is absorbed. If this radiation is absorbed, naturally it will not come out, and when it does not come out at the corresponding opposite position on the photographic plate, once again because of no incidence of radiation, that much part would remain black. So here also we get black line. Similarly, if this is getting absorbed at corresponding opposite position on the photographic plate, we will get black line. Such extremely thin black lines are obtained in this spectrum, but such lines are obtained after the absorption process. After absorption process. That's why such a spectrum is called absorption spectrum. Absorption spectrum. Correct? Fine. And at all other regions other than these black lines on the photographic plate, because of incidence of radiation, that much part turns out to be white. Correct? In the emission spectrum, there were white lines between black regions. Here there are black lines between white regions. Got it? Fine. Now these black colored lines are given a specific name. They are called Fraunhofer lines. Fraunhofer lines. Okay, fine. In the textbook they are given one very good example of this absorption spectrum. What is the example? I am showing you. Here is the central part of sun, and here is a surrounding layer, say surface of sun you can say. It is called photosphere. It is called photosphere. And surrounding to photosphere we have a layer of gases in which there are atoms which are shown here by dots. Okay, fine. Now it so happens that when solar radiation is emitted from this photosphere, it has continuous wavelengths, that is all possible values of wavelengths, correct? But when that solar radiation is coming out of this photosphere and made incident on the surrounding atoms, it so happens that these surrounding atoms absorb certain specific radiations with specific wavelengths. So naturally, when those radiations are absorbed, they will not be passing through this external layer, And that's why when we get that solar radiation emitted from sun onto the earth, then on that earth you will not have those radiations which are already absorbed here, correct? The absorbed radiations are missing on the photographic plate, and that's why corresponding to those absorbed radiations at corresponding positions on the photographic plate, you will have Fraunhofer lines, that is black colored lines, because those radiations are already absorbed here, they are not in a position to reach the earth. Okay, so what spectrum we get of solar radiation on earth, it is not emission spectrum, it is absorption spectrum. It is absorption spectrum because it contains Fraunhofer lines, it contains black lines. Got it? Fine. Now let us see some very good points of difference between emission spectrum and absorption spectrum, not given in the textbook. Very good question, worth asking for any examination. Look here. Points of difference between emission spectrum and absorption spectrum. First point, here spectrum is obtained by emission of radiant energy. By emission of radiant energy. Here spectrum is obtained by absorption of radiant energy. Fine. Second point is this, here atoms are excited before emission. Before emission, atoms were lying in excited states. Here, before absorption, atoms were lying in the ground state. Correct. Third point is this, emitted radiations have definite wavelengths. Here, definite wavelengths are possessed by emitted radiations, and here, absorbed radiations have definite wavelengths. Here, radiations with definite wavelengths are emitted. Here, radiations with definite wavelengths are absorbed. Then last point, here spectral lines are white, spectral lines are white, and here spectral lines are black, which are called Fraunhofer lines. Here majority region on the photographic plate remains black. Here majority region on the photographic plate turns out to be white. Okay. So these are some very good important points of difference between emission spectrum and absorption spectrum. Okay, please prepare all these points. Okay. Now in the illustration number 8 in the textbook, they have used one formula. They have used one new physical quantity called reduced mass, but nowhere they have explained anything about that. So let me make it clear first, and then we will proceed for that numerical. Okay, what is that? I am showing you. Consider a system of two particles which are rotating about common axis of rotation, which is passing through their center of mass. Such a system we call binary system. We call binary system. Okay, fine. For this binary system, let us find out kinetic energy. Come on. Take this particle with mass m1, take this particle with mass m2. Because this mass is heavier, then center of mass is closer to this heavier body. Correct? So this center of mass is away from lighter body, closer to heavier body. And now this is an axis passing through the center of mass, about which both the particles keep on rotating with constant angular speed. Such a system is called binary system. Fine. This much distance I am taking as r1, this much distance I am taking as r2, and total distance between these two particles I am taking as r. Now, what is the total kinetic energy of this binary system? It is kinetic energy of first particle plus kinetic energy of second particle. What is kinetic energy of first particle? Half m1 v1 square. For second particle, half m2 v2 square. Simple. This 1 by 2 m1 as it is, don't you know? v1 equals to r1 into omega. So v1 square will be r1 square omega square. 1 by 2 as it is, m2 as it is. What is v2 square? v2 equals to r2 into omega. So v2 square will be r2 square omega square. v2 square will be r2 square omega square. 1 by 2 omega square, 1 by 2 omega square. This much part I can take common. Inside the bracket left is m1 r1 square plus m2 r2 square. Half omega square is as it is. Come on, m1 as it is. What is the formula of r1? In second semester in the first chapter on center of mass, you had studied the formula of r1 and r2, and those formula were, for r1 it was m2 into r upon m1 plus m2, and for r2 it was m1 into r upon m1 plus m2. Remembered? Fine. So this m1 as it is, what is the formula of r1? Formula of r1 is this, m2r upon m1 plus m2 whole square. m2 as it is, formula of r2 is m1r upon m1 plus m2 whole square. Here also total distance upon total mass, here also total distance upon total mass. If it is r1, then here it will appear m2. If it is r2, here it will appear m1. Fine. Now just simplify. 1 by 2 omega square as it is. Come on, r square upon m1 plus m2 whole square. That much part I can take common from both the terms. R square upon m1 plus m2 whole square. What is left from here? m1 and m2 square. What is left from here? m2 and m1 square. Now 1 by 2 I am writing as it is. Come on, r square omega square, that I have written here, r square omega square. Now from these two terms in addition, I can take which part common? m1 into m2, m1 into m2 I can take common. So that common part I have written here, m1 into m2 divided by m1 plus m2 whole square I have written here. And when you take m1 into m2 out, left from here inside the bracket is m2, left from here inside the bracket is m1. Fine. So now tell me, this 1 by 2 as it is, this m1 m2 upon m1 plus m2, see 1 m1 plus m2 is getting cancelled, 1 m1 plus m2 is getting cancelled, correct? And when it is getting cancelled, left is m1 m2 upon m1 plus m2 into r omega whole square, r omega whole square. I repeat, this much part is getting cancelled. See m1 plus m2 from here and m1 plus m2 from here, correct? Getting cancelled. So left is 1 by 2 m1 m2 upon m1 plus m2 into r omega whole square. And now tell me, 1 by 2 as it is, this much bracketed part has the unit of mass. How? Kilogram into kilogram will be kilogram square, kilogram plus kilogram will be kilogram only, kilogram square upon kilogram will have unit kilogram. So this bracketed term, because it has unit kilogram, must be indicating some sort of mass, which we have shown here by symbol mu. It is called reduced mass. What is it called? Reduced mass. It is shown by symbol mu. And don't you know V equals to R omega? So in place of R omega I can write V. So it is V square. So this formula is very much like kinetic energy is half mv square. Half mv square. Instead of m, I am putting mu. But remember, mu is called not mass, but it is called reduced mass, which is to be defined only for a binary system. Which is to be defined only for a binary system. Don't forget, in place of which bracket you had replaced this mu, you had placed this mu in place of this bracket. Come on, m1 into m2 upon m1 plus m2. This is called reduced mass for a given binary system in which there are two particles having masses m1 and m2. Okay, fine. Now, this formula we will utilize in the next illustration. So now please remember this formula. Okay. What is mu? I repeat, reduced mass. What is the formula? Mu equals to m1 into m2 upon m1 plus m2. Now, read the illustration number 8 now. Come on, have you read it? Fine. What is given to us? One positronium atom. positronium atom. And in that there are two particles having identical masses, but one is having charge positive, another is having charge negative, and each of the charge has magnitude 1.6 into 10 raised to minus 19 Coulomb. One such particle having positive charge is called positron, another particle having negative charge is called electron. Positron and electron, they are antiparticles of each other, having same masses, same magnitude of charge, but opposite polarity. One is having positive charge, another is having negative charge. Okay, they have same mass. So M positive is also M, M negative is also M. This is mass of positron, which is I am taking M. This is mass of electron, which is also M. They have same mass. Fine. Now what do? They just rotate about this axis, which is passing through their center of mass. Right now it is passing through the geometrical center because they have same mass. So this central line becomes the axis of rotation. And now this distance, if I am taking R, this is also R. So total distance between these two particles would be R plus R, that is 2R. Okay. Let us first of all find out reduced mass for this binary system. Mu equals to M1 M2 upon M1 plus M2. As per textbook symbols are written here, M positive into M negative divided by M positive plus M negative. M positive is mass of positron, which is M. M negative is mass of electron, which is also M. M plus M, that will be 2M. Now 1 M is getting cancelled. 1 M is getting cancelled. Correct? Come on. 1 M is getting cancelled. Now left is 1 by 2 M. 1 by 2 M. Fine. And tell me, when this system is set into rotational motion at that time, this is rotating about this, correct? This way, with radius of the circular path equal to 2R, and this is rotating about this, correct? This way, with the radius equal to 2R. Got it? Fine. Now tell me, if this particle is rotating, I mean performing uniform circular motion, there must be some centripetal force. Let it be Fc. Actually it is provided in the form of electrostatic force of attraction by electron on this positron. So that is, the centripetal force is provided in the form of electric force. Fc means centripetal force and Fe means electric force. What is centripetal force formula? mv square upon r. Say mv square upon r. But in case of binary system, don't say m, say mu. In place of mass m, you must take reduced mass mu. So mu v square upon r. R is the distance. But distance between these two particles, it is not r, it is 2r. Okay. Instead of m, you will write mu. mv square upon r. Instead of r, you will write 2r. Total distance is 2r. And that force is provided in the form of electric force. Electric force obeys Coulomb's law. According to Coulomb's law, what is Coulombian force? K Q1 Q2 upon R square. Instead of K, I have written 1 upon 4 pi epsilon 0. Q1 is magnitude of charge of positron, which is E. Q2 is magnitude of charge of electron, which is also E. And divided by square of distance between them. Come on, distance between these two is 2R. Its square would be 4R square. Simple. Now tell me what you can cancel. Can you cancel R? Can you cancel R? Yes, we can cancel R. So now tell me 1 by 2 mu v square. 1 by 2 mu v square. E into E is E square upon 4 fours are 16 pi epsilon 0 R. E square upon 16 pi epsilon 0 R. And now let us find out total energy of this positronium atom in the ground state. Let it be capital E. Total energy means kinetic energy plus potential energy. What is kinetic energy for a binary system? Just now we obtained the formula 1 by 2 mu v square. Come on, 1 by 2 mu v square. By mistake in the textbook they written here 1 by 2 mu r square. Actually it must be 1 by 2 mu v square. Plus, what about potential energy? It is K Q1 Q2 upon R. Instead of K I have written here 1 upon 4 pi epsilon 0. Q1 is charge of positron, which is plus E. Q2 is charge of electron, which is minus E. I told you in the formula potential energy, you must retain the polarity of the charge as it is. Okay, so charge of electron is negative, so I am writing here minus E. divided by distance between two particles. Distance between these two particles is right now 2r. So I am writing here 2r, correct. Now tell me, half mu v square formula we have kept ready, square upon 16 pi epsilon 0 r, square upon 16 pi epsilon 0 r, plus minus e into e, that is e square, 4 to the 8 pi epsilon 0 r, pi epsilon 0 r, correct. From these two terms, what part you can take common? Square upon 8 pi epsilon 0 r you can take common. Left inside the bracket from here it is 1 by 2 minus left inside the bracket from here it is 1. 1 by 2 minus 1, what is it? Minus 1 by 2. When you multiply by here, then you will get E value, come on, minus E square upon 16 pi epsilon 0 r. Let it be equation number 1. This is the total energy of positronium atom in the ground state. And now we are supposed to compare that energy with the energy of a hydrogen atom in the ground state. And that formula, actually in Bohr's atomic model we had obtained, total energy of hydrogen atom in the ground state is minus E square upon 8 pi epsilon 0 r. Give it equation number 2. Just multiply this right hand side by 1 by 2. If you multiply on both the sides, say by 1 by 2, then here it is 1 by 2 EH, and when you multiply 1 by 2 here, it will become minus E square upon 16 pi epsilon 0 r. But minus E square upon 16 pi epsilon 0 r is nothing but E. So when you multiply by 1 by 2 on both the sides, this right hand side becomes E, correct. So E equals to 1 by 2 EH, E equals to 1 by 2 EH. That is, total energy of positronium atom in the ground state is half of the total energy of hydrogen atom in the ground state. That is what we have proved. E equals to 1 by 2 EH. What about wavelength? I am showing you. EI minus EF according to second postulate in Bohr's atomic model is H into Fik, H as it is. Don't you know C equals to F lambda? So F is C upon lambda, fine. Now take this lambda Ik in the numerator, take this difference in the denominator. So lambda Ik is proportional to 1 upon EI minus Ek. Now take this as ionization energy, take this as ionization energy. Then from here we know ionization energy for positronium atom is half of ionization energy for hydrogen atom. So when the energy is half, when this energy is half, naturally this wavelength will be doubled. So wavelength of emitted radiation from positronium atom will be double than wavelength of radiation emitted from hydrogen atom. Got it? Fine. Because this energy for this positronium atom is half, because this energy is half, naturally this wavelength will be doubled. Got it?